Good morning, this is Jim Chastain with EasyPower. This is our second refresher episode in the device coordination series. Welcome all. As I mentioned last week, this is a multi-part series designed to be in more bite-sized capsules that may be easier to absorb. And today we're going to focus on toolbar and controls and some of the questions that came up from last week. And if any of you have questions, please enter them on the chat bar or send me an email, jim@easypower.com, and we can follow up later. So as I mentioned, last week we essentially went over the basics of the display, the power protector screen module, and what constitutes the ribbons, the icons that change when we go into focus for coordination, and specifically what type of curves are produced for different types of elements, protective devices, transformers, motor loads, and the like. We also talked specifically about two ways of temporarily adjusting the settings. One is click and drag the curves themselves, and then the second, to be able to open up a temporary dialog box for that element and then be able to make adjustments or look at the impact on the system if we considered using a different size or different characteristics of device or even loads, and kind of a what-if scenario analysis. One of the things I wanted to do today was tie in some of the aspects of arc flash calculations, and in some regards even some misunderstandings that folks even still have that have not had much experience with arc flash. I'm going to start off with a very simplistic example and then use the power protector module to identify visually and see what's going on, as opposed to just using the spreadsheet output. That's part of an arc flash calculation scenario. So one of the things that I emphasized last week, and it still continues to, it comes up very frequently, is you cannot change from a database focus into any of the other analytical modules until you have a clean OneLine diagram. And so you'll see that as you kind of get into the tools, and anytime you're going into a new analytical module, whether it's short circuit, arc flash, or coordination, power flow, and the like, my advice is to start with a very simplistic circuit at first so you can control all the different aspects and make sure that you have a handle on what the procedure is or what the calculations that are taking place before you get hung up on trying to analyze a big system. So I'm going to start with a very simplified example, and it was very helpful for me in the early days of trying to understand arc flash, because it's a comparison between bolted fault current, where arc current comes from, how the arc time is calculated, and then as we're using the coordination module, being able to look at the impact of and the relationship between these different elements and how to take advantage of some of the key features in the TCC displays. So with that in mind, let's kind of go to the tools. And here's a very, as I was mentioning, the very simplistic example that I like to start with, especially for folks that don't understand arc flash. And I ran into a question here last week where I was talking to a electrical maintenance manager at a semiconductor plant, and I was trying to understand where arc flash compliance ranked on his scale of priorities, and his response was, we really don't have too many motors in the system, so I don't think we need to worry about arc flash. and that brought this particular example to mind. This is an example of a circuit that I had a discussion with on the phone a couple years ago, specifically with an electrician in Oklahoma who was working on labeling the electrical stack above some downhole pumps, and he was concerned that the tools were giving him incorrect information. So what he has was a utility feed into a transformer. The utility comes in at 12.8, 1000 kVA transformer, and he has a 480 volt distribution. And as far as his model, he only has two cables, one a very short one at 50 feet and one a very long one at 1,000 feet. And he said, let's just disregard the pumps that end up being at the connected to these cables. I just need to label these particular intersections. Okay. The neat thing about this example and the reason it's so ultra simplified is there's only one protective device. So what we're doing is making a comparison between the same energy source, the same protective device, the same cable construction, with just a difference in impedance. And so as we go into short circuit analysis and calculate the voltage fault current on a three-phase hard fault or three-phase balance fault, we see that if this bus were to fault, we'd have 20,915 amps. If this bus were to fault, it would experience 17,925 amps. And if this bus were to fault, it'd see 4,479. Now this is all symmetrical arc bolted fault current balanced, and the next step in the operation was to calculate incident energy. And we see that this has an incident energy of 3.6 calories per square centimeter at 18 inches working distance, which gives us a 38-inch arc flash boundary, whereas this particular bus, which is 50 feet down the road, gives us a 3.9 calorie per square centimeter incident energy density at a working distance of 18 inches and a 40-inch arc flash boundary. Whereas if we go the other 950 feet, the arc flash boundary has doubled and the incident energy has almost tripled. And so me and this electrician both started scratching our heads because we knew that there's only one energy source in the system, and it's a transformer. The farther away you get from that energy source, the lower your energy ought to be. And so his assertion was there's a problem with the software. Well, it turns out this is where the tools come to great advantage. If we look at the both arc flash spreadsheet and the OneLine diagram, we can see that with the same element protecting all three buses and the same type of bus described, each bus will have the same air gap, and we've already identified the bolted fault current, but in each case there's an arc fault current different for each one. This particular calculation is key. There are currently 4 equations in the IEEE model. One of the equations is specifically to produce this number, which is the arc flash current based upon the air gap, the voltage, and the available bolted fault current. And so IEEE has characterized the reactive and resistive impedance of an arc, a plasma arc, and consequently been able to model the calculation of arc current given these other parameters. So the tool allows us to compare now the resulting arc current, and for now, if you'll notice, each of these is in magenta, and I'll come back to that in a second. But consequently, now that we have the arc current calculated, we can look at the curve for the fuse and understand the trip time. And it turns out the trip time is what creates the biggest difference now between these 3 buses. The bus with the much lower arc current has a much higher or longer trip time, and consequently all the energy is going to be basically released in almost 1.4 seconds, which is 10 times as long as the arc that would exist in either of these other two buses. All right, so to visually see this, we can go to the coordination module, and as we do that, we can project or present the trip characteristics of this particular fuse. So it's an AB chance fuse link size 12, and just in and of itself, it's not doing much for us, but you can see that as we look at the axis on this particular plot, we have time along the vertical axis and then current along the horizontal. This particular current is amps at 12.8 kilovolts, and so as I watch right down here in this area of the screen, as I place this cursor over the trip curve, you can see right now at 330 amps, the fuse will start to trip in 0.101 seconds. And so this will tell us, based upon knowing what the arc current is through the fuse, what the trip time is. Well, as it stands, we can't predict or show what the trip current is at the individual buses. So let's go back and look at the whole system and plot. All right, so now what we see is that the trip characteristics, performance, this is specifically the TCC curve of the fuse. We also see that the characteristic damage curve, inrush characteristics, and frequent fault curve for the transformer. We also have both cables plotted here, and as we go in and look at this fault, we fault that particular bus, we can see that the maximum current through the fuse is 798 amps, while we have 17,925 volted fault current through the bus. If we come over here, right-click on and so this is a feature of coordination module. If I right-click on the curve and insert the arcing tick mark for the current, this shows us specifically where this current would produce 326 amps in the fuse itself, and this time of 83 milliseconds, if we kind of look at where the curve intersects, the maximum delay is 73 milliseconds, and it first starts to melt. Take that back. First starts to melt at 82 milliseconds, and it is guaranteed to clear in 119 milliseconds. So we're still on, as far as the display, we're still on a 480 volt basis, but we're seeing the arcing current as it relates to the 12.8 kilovolt environment of the fuse. If we fault this other bus, which is a much lower current, you can see that it actually clips at that maximum current, and if we try to insert here the arcing mark, it'll be essentially cut off by the way we've displayed it. All right, so the point being that we can physically see how current literally crosses the boundary even of a transformer in the voltage ranges by looking at the way that the plot is made and the individual arcing currents at each bus. Okay, now, so there's one other thing to point out here, and that goes to the difference between, well, let's go back over here and plot the arcing current. So to do this, I fault this bus, I right-click on the curve, insert the arcing tick mark, and this is the 85% arcing current. All right, the significance here is the 85% versus the maximum current for that bus. And the reason for that specific calculation is a requirement of IEEE to take the worst case between 100% and 85% and compare them for tripping time. Okay, so let's close this, go back to my short circuit calculation, fault the bus, and look at my arc flash results. When we see an arc flash hazard spreadsheet that has magenta figures in it, that means that the calculations are being made with the 85% fault current for the protective device. So that's essentially the tools doing the adjustment for us, and we can see it both in the short circuit environment and in the display of the fuse versus a fault on a particular bus. Okay. I think I've kind of beat that one to death, but significance here is time is critical in arc flash. The elements that control time are the protective devices, and so even in a very simplistic example like this, it's important to understand what the tool is doing for us and how to get the results out of it that are useful for a number of reasons. All right, let's go to a more, say a less simplified example and look at some of the other features in the TCC display. There are a number of elements we can control, and let's start with doing a short circuit to make sure we have a clean system. We get bolted fault currents. We go into the coordination module, and we're going to plot a motor load, 1, 2, 3, 4 breakers, and a transformer. And as we do this, we have the ability, as we already kind of discussed, we have a couple different displays that are beneficial for a number of reasons. One, the OneLine diagram shows the elements that have been highlighted. This is shown both on the OneLine diagram and the display. As we make adjustments in the OneLine diagram, they get reflected on the inset, and so consequently this makes for a better report in a single sheet format. We can also customize the curve and legend labels at the bottom with your logo and some basic information. These can be displayed in the title block and in the OneLine diagram, or not, depending upon how much room you want to take up on the screen. We talked previously about how to make adjustments. As we hover the cursor over a particular curve, we see the set points of the trip unit displayed on the inset box, and as we left click and make adjustments, those settings, the tool only allows us to go to places where the datasheet has finite set points, and as we make those adjustments, the new settings are displayed. If we right click and show original curve, we can see where we started off as we made this particular adjustment. Likewise, we can make adjustments to the curve by shifting a fixed amount. So we can shift it by 87%. We probably can't see as much until I use a larger set point. So you can see this dotted line here is the shifted curve, the curve shifted by 173%. I'm not sure if you can see that dotted line that shows up. We'll do it again. So I'm going to shift the curve 58%, and it's right here. So this is the 58% setting for, you can see the green line. So I can make an adjustment and shift the curve 87%. The green line moves to here, and if I click off of it, it becomes a purple dotted line. I can shift the curve a fixed amount, 115%, and now it shows up 15% to the right. Okay, and then on top of that, we can show where the original curve, we're actually on the original curve. And so now you see the 15% marker shifted with me as I move the curve. Okay, these are all a function of highlighting the curve in the TCC display, and then right click and select shift the curve or modify. If we go to modify, again, it'll change the direction of the shift, and we can do it a finite change rather than a fixed number. Okay, so I also wanted to show arcing current in this particular setting display. So here we've got, as we select the OneLine diagram display, highlight a bus and fault it, you can see that this particular current that's going to this bus, none of it comes from downstream. So this particular breaker, which is BL2FC, is really not in play when it comes to limiting the current, either bolted fault or arc current, to switchgear 2F. If I select the curve for 2FA, right click and insert arcing tick mark, you can see that here you can see our maximum arcing tick mark is 17,966 amps, which is the maximum arc current that will be created on the physical dimensions of this bus with 480 volts applied and this much available current. Now, if I make an adjustment to this setting, you can see that my arcing current goes away, and what's happening is as soon as I do that, the worst case current becomes, I've now entered the point where my 85%, let me kind of go back and show that. So what the tool is doing is calculating and giving me the option of using either the 100% arcing current or 85% arcing current. And so that's going to be somewhere down in this area. As soon as that 85% mark, if I adjust the curve to the right, that the 85% mark falls now into this vertical section, my worst case trip point now becomes a much higher value. And as we're calculating incident energy, you can see that it basically goes through the roof. So as I adjust this back so that my 100% arc current is used for the calculations, it becomes a much more reasonable number. And we'll see this in the, all right, the point I'm trying to make is a correlation now between this 100% calculation and what we're seeing in the arc flash incident energy. As I close this curve, let's not plot it, and I go back to short circuit, I fault the buses, and I want to specifically look at the arc flash for that bus. You can see that this is in black type, and it's got a maximum arc current of 17,966, which is what we were showing on the curve. As I go back to the coordination module, we pick up that same group of elements, plot the curves, I want to fault the bus. Now as I fault the bus, and I made the adjustment there before I showed it off, here's my 17,966. As I adjust this curve such that I know the 85% point now is what's taken effect, I can go back and look at my arc flash incident energy calculations, short circuit, fault this bus, look at incident energy. Now you can see the type is magenta, and that's because we're calculating 85% of the maximum fault current, which gives us a slower opening time. So again, some of this stuff you don't see directly, but the tools are doing this calculations for us behind, and it's important to understand what we're being shown both on the arc flash spreadsheet and in the coordination module. Okay, so to me that was something of an epiphany, so hopefully it's helpful to those in the audience. Let's see what else we got here. Okay, the breaker on both the primary and secondary transformer on a fault occurs downstream of the secondary. Can show how they interpret the reflected current on the primary of the transformer with respect to which OCPD will trip first. Okay, the answer is yes. If I can set up the example. So if there's a breaker both in the primary and secondary of a transformer and a fault occurs downstream of the secondary. All right, so that's what we have set up right here. Here's the downstream on the secondary, and here's the upstream. Let's go ahead and fault these. Go into coordination, plot the curves, and again I can manipulate and calculate incident energy here. As I don't select any bus and I fault the buses, then all the buses get faulted, and consequently we see the incident energy. If I pick a specific fault, oh, actually, let's kind of go back to where I was, my second point that I wanted to make as far as the agenda. All right, what we're talking about is a more complex system. And let's say if I have this particular bus fault and we want to calculate arc flash energy and see where the resulting breakers will trip, I fault the buses. I've selected a specific bus, fault the buses. I want to look at current, and as I do that, I can also look at a sequence of events. So I've selected a single bus, faulted it. I'm looking at the current, branch current, in this case momentary. I can look at sequence of events, and the tool now tells me that if this bus faults, this device will trip in 340 milliseconds on the secondary side. This device will trip in 683 milliseconds. And then this device will trip in 123 milliseconds. This is red, obviously, because this is miscoordinated, or it trips quicker than the downstream breakers, and that may or may not be a good thing. Certainly, it doesn't follow the standard rules of coordination. So let's see if I answer the question. Okay, now how does that, so the reason I do that is to make sure that I know what I'm adjusting as I'm calculating incident energy. For instance, and we do that by going back to the module, highlighting all the elements, and plotting them. And what we're showing here is now we're including the upstream relay. We're going to fault this bus and calculate incident energy. And as we're looking at this, here's the downstream breaker, so it really doesn't have any effect. So we can essentially take it out of there. The motor is a good thing to look at, RA6. So what our sequence of events told us is that this is the element, the relay upstream is the element that's actually controlling the incident energy here. I can verify that by making adjustments on this downstream breaker, and you can see on this breaker right here, BL2FA, and you can see where it was currently set, it doesn't have any effect. It's only when I exceed the settings of the relay that now I'm actually changing the arc flash calculations. So to answer the question, to see what the effect is or what the result is, if I'm in this mode and I'm trying to mitigate energy here, the controlling element is going to be this breaker upstream or the relay upstream by the transformer. And so let's see if we can make an adjustment there. So let me put this breaker out of the way where it started off. And we're going to adjust the relay. And so you can see now as we change the relay settings, it's going to affect the incident energy calculated for that particular bus. So likewise, not only is it miscoordinated, it probably was getting in the way of trying to protect the other downstream elements. And so in reality, I want to have this breaker set up so that it's now protecting this particular bus. I can see the difference. Well, so I guess that kind of answers the question. Let's see if I got another question. Okay. Appreciate the feedback on the sound. All right, so that was the only question that we had so far. We talked about the arcing current. Here's a good point. So I've faulted this bus. If I try to, and again, we're looking at the BL2FC, the downstream breaker. If I try to show an arcing current, because it's not part of the short circuit, it's not going to allow me to show the arcing current. I'm going to delete this to take it off the screen, highlight this, and I can put my arcing current tick mark here. And here is where the arcing current, 100% arcing current, will start to engage the pickup on the trip mechanism. And here's where it's guaranteed to clear. And you can see the results down here on the toolbar on the bottom. So that the trip settings will be between 157 milliseconds and guaranteed to clear at 151 milliseconds, 159. All right. Likewise, now you can see that we have a difference now between our upstream relay. Okay, this brings into play as I select two different curves. I want to produce a fault calculator, a difference calculator by selecting two curves, and now I can see what the difference in coordination is, or trip settings for incident energy at a particular fault current, and here at the arcing current that we've calculated for this particular bus, we see we have a clearance of a little over half a second, 0.688 seconds, between this downstream breaker and the relay. Now the other question is, where did this breaker go, or where did this fuse go? And at that point I'm going to fault all the buses again. And so what we're looking at here is FS3A, which is this fuse.